All right, section 4-8 is on the derivatives of implicit relations. We call this implicit differentiation is the technique we use. The objective of this section here is, given the equation of an implicit relation, find the derivative of y with respect to x. Now, if you recall, actually, you've seen implicit differentiation. We've just kind of briefly covered it in a couple of sections previously. Actually, you first were introduced to it back in Chapter 3. The end of Chapter 3, we wanted to find the derivative of the natural log function, and so we used implicit differentiation there. And then actually earlier in this chapter, with the derivatives of your inverse trig functions, to find the derivatives of those functions, we also used implicit differentiation. So we're going to dive into it a little bit further here in this section. All right, so let's start off with just some terminology here that we need to understand. And that is the difference here between an explicit relationship and an implicit relationship, as the objective indicated. And that really helps us understand why we call it implicit differentiation. An explicit relationship, or explicit relation here, is an equation which is solved for y. So a lot of functions that we work with are already solved for y as a function of x, and so we work with a lot of explicit relationships. So for example, something like y equals x squared plus sine of x, or whatever. As long as you have all of the x's on one side and you have just a lone y on the other side, you have an explicit relationship where it's solved for y. Now, an implicit relationship is where you have an equation that is not solved for y. So we haven't seen very many of those, but again, as I mentioned earlier, when we were working with the derivatives of your natural log function and the derivatives of your inverse trig functions, because we had to rewrite those in order to find the derivative, turned out the way we rewrote those equations is they were no longer solved for y, so we had actually an implicit relationship, so we took the derivative implicitly. So let me give you an example of this. Something like x squared plus y squared is equal to x times y. Again, you can clearly see here it's not solved for y. And when we say it's an implicit relationship and when we say it's not solved for y, it doesn't mean that it has to be solved for x then. As you can see, this is not the case in this example. It just means that it's not solved for y. All right, so let's take a look now that we know what an implicit relationship is. Let's take a look at implicit differentiation. And implicit differentiation is referring to taking the derivative of an implicit relationship. So technically, all the derivatives that you've learned so far and have worked with so far, if we want to get technical about it, they've been explicit differentiation that we've been doing, because you've been working with explicit relationships and finding the derivatives of those explicit relationships. We would call that explicit differentiation. But we usually don't. We just simply refer to it as differentiation. It's only when it's not solved for y that we refer to it as implicit differentiation, to indicate that it's not an equation that's solved for y. But I can still take the derivative of that equation, regardless of whether it's solved for y or not. Here's the technique that we use. The first step here that you need to do for any function, I guess, that you want to take the derivative of, whether it's implicit or explicit, is you want to differentiate both sides of the equation with respect to x. So in other words, we want to find the derivative of both sides of that equation. Of course, anytime you have an equation, whatever you do to one side, you have to do the same thing to the other side. So when we say we're taking the derivative of both sides, in previous equations where you had y equals something, an explicit relationship, you took the derivative of y, which we call y prime, and then you write equals, and then on the other side you took the derivative of your equation and write what the derivative is. So you took the derivative of both sides of every equation you've worked with so far. This is nothing new to us. One thing we got to keep in mind, though, or remember here as we're going through this, is the following. Whenever we take the derivative, that's d dx there. That notation, remember, means the derivative, or find the derivative here. So that's saying the derivative of x. If you want to find the derivative of x with respect to x, remember we can actually rewrite that by sliding that x into the numerator like we see over here. I've taken this x and I've slid it up here into the numerator. And so I end up with dx over dx, which of course That's this one quantity over the same quantity, so that's equal to 1. So anytime you take the derivative of x with respect to x, you get 1. In fact, that's true for any variable. Anytime you take the derivative of a variable with respect to that same variable, you'll always get 1. On the other hand, for any other variable, like for example, over on the right here, we have the derivative of y with respect to x. Again, this notation here is our derivative notation. It says find the derivative of y, or the derivative of y is. And I can take that y, just like I did over on the left there, and slide him up there into the numerator. So I have dy dx. So I don't get 1 in this case. I get dy dx. It's not the same thing in the numerator and denominator, so things don't cancel out. And dy dx is just another name that we use for y prime. So all I got to remember is that when I take the derivative of something that involves y in this process, that I need y primes to show up. And again, going back to all the derivatives you've done so far, that's exactly what you've done. Whenever you take a derivative of some equation, y equals something, you took the derivative of y on one side and wrote y prime. That's exactly why we write that down, because you took its derivative. And then you did the same thing to the other side. So again, there's nothing new here that we're learning. It's just a kind of reminder of the specifics of the rules we've been following. All right, so the first step is to take derivatives of both sides, and once you do that, you'll then end up with, well, x's and y's and some y primes all over the place in that equation, or potentially all over the place. And we're trying to find out what the derivative with respect of y with respect to x is. We're trying to find out what y prime is equal to. So the next step of this is to solve the derivative equation for y prime in terms of x and y. In other words, just like you've worked with algebraic equations all the way back to algebra, where you had some unknown in there, in our case it's going to be called y prime, the way that you solve for that y prime, or that unknown variable, is you get all of those variables on one side of the equation, everything else to the other side, do a little bit of factoring, and then solve for your unknown. Okay, we're working with a linear equation in terms of y prime. So it's going to be relatively easy for us to solve for that y prime, just like you did way back in early days of algebra for you. That's the process. There's really nothing new here for us. The only thing that's new for us, I guess, really, is that second step that before, when you took a derivative, it was already solved for y prime. You already had y prime by itself. You don't have that with an implicit derivative, so you have to take the extra algebraic steps to get y prime by itself. Otherwise, there's no new rules here for us to follow. All right, so let's try a couple of examples. Look at example 1 there on page 170. And it says, consider the implicit relationship x squared plus y squared is equal to 25. And they give you a sketch of that over there on the right. And notice that's the equation there for a circle centered at the origin with a radius of 5. And it says, for part A, explain why the graph is a circle. Well, again, that's you're going back to your understanding from conics and pre-calculus. We've seen that that's our standard form for a circle centered at the origin with a radius of 5. So we've really answered that already. I'm just going to jump past that now to part B. It says differentiate implicitly to find dy dx. Okay, so for part B, we're going to take the derivative with respect to x of this equation. Derivative with respect to x, so d dx of that whole equation. And again, remember those rules that we just went over there when we go to take this derivative. When I take the derivative of x with respect to x, I get 1. Derivative of y with respect to x is y prime. All right, over on the left side here, I have a sum of two functions, x squared plus y squared. So just follow the rules you already know for derivatives. You take the derivative of the first function, and then you add it to the derivative of the second. So let's start with x squared. Derivative of x squared is just 2x. Now for the y squared, think of this as being a composite function, where you have an inside function being y and an outside function being the squared power, and take its derivative. Okay, this will help you remember to get the y prime to show up in the right spot here for us if we follow chain rule to do this. So derivative of y squared is going to be 2 times something raised to the first power. That's the derivative of the outside function. Chain rule says you substitute in the inside function, which is y. And then finally, you multiply by the derivative of the inside function. And you can call that y prime, you can call that dy dx, whatever notation that you use. I'm going to write it as dy dx in this case, but you can write it either way. It doesn't really matter since they said define dy dx. That's the reason I'm going to write it that way. But you can also write it as y prime. The key is if you're going to use y prime, then don't be writing y to the first power, like you can see that I've written there, and next to it. Otherwise, you can get confused as to whether it's a derivative or whether it's just y to the first power. On the right side, take the derivative. You've got a constant. The derivative of a constant is just 0. And they wanted us to find out what dy dx is, so here I have an equation. I have this unknown right here, and I want to solve for it. So again, just go through the rules that we already know from algebra to do that. Take the 2x, and let's move him to the other side. So you'll have 2y times dy dx is equal to, I'm going to subtract the 2x to move him over to the right. And now, to get rid of the 2y, that factor of 2y out front, just divide both sides by 2y. So I'm going to have dy dx is equal to a negative 2x divided by 2y. And actually, you can see that the 2's here are going to cancel out. So I can actually write this as the opposite of x over y. You'll see our answer here is written in terms of x and y, which with a implicit derivative, we said that's okay. And it's okay because of the fact that our original equation was not solved for y, and so therefore it's okay if our derivative is in terms of both x and y. All right, so that's part B on this one. Part C said to calculate the two values of y when x is equal to 3. So we're going to go back to the original equation that they gave us for part C. They told us that x is equal to 3, and they wanted us to find out what y is equal to. Well, if I go and plug in what that x is equal to 3 in that original equation they gave us up here, x squared plus y squared equals 25, I'll end up with 3 squared plus y squared is equal to 25. And let's just solve this thing for y. So subtract the 3 squared to move him to the other side. 3 squared, of course, is 9, so I'll have y squared is equal to 25 minus 9 is 16. And to take the square root of both sides, don't forget you get a plus or a minus. You get two solutions here. Y equals plus or minus 4. Which again, if you look at the graph they gave you here of this circle, you'll see that x equals 3. There's 2 points. There's 1 point up above in the first quadrant at x equals 3. Y is equal to 4 up there. And in the fourth quadrant, when x is 3, you can see there's a value in the circle of negative 4. So that makes sense that we should get two solutions there. And then finally it says for part D, draw a line with slope dy dx through the point through the point found in part C with the lower value, so they're talking about the negative one here, lower value of y. And how is this graph, or how is this line related to the graph here? Okay, so let's first find the slope of that line. Again, I want to find the slope at x equals 3, negative 4 is the point they gave us, the lower y value they said. So I need to find the derivative. I need to know the slope of this thing. Well, right here was our derivative. We said the derivative, dy dx, is equal to the opposite of x over y. So dy dx is equal to the opposite of x over y. So all I got to do is substitute in my x, which is 3, and my y, which is a negative 4, and that'll tell me the slope here. So it's equal to a negative 3 over a negative 4. Or that turns out to be just 3/4. So the slope there is positive, which again, if you look at the graph there, they gave us that circle. And you can see that at x equals 3, y equals negative 4, the slope there should be positive based on that curve. And we can sketch what that looks like here. I'm just going to roughly sketch it. If you wanted to get a little more accurate sketch, you certainly could do so, but I'm going to just roughly sketch that. That wasn't a very good circle, but that will work. This we're going to say is 3, and that is negative 4. So what we just found is that at this point here on our circle, if I were to sketch in the tangent line, something like this, that the slope of that tangent line is equal to 3/4. Okay, that's what the derivative always tells us. It tells us what the slope of our tangent line at that point on the curve is equal to. And so that's the line that they're talking about with slope equal to dy dx, or 3/4 in this case. All right, so you'll notice that in order to find the derivative at a point, there's a little bit more involved as well with this process, because of the fact that I have to know usually both an x and a y value to plug in, which is why they had me in the previous part of this find the corresponding y value. All right, so let's take a look at another example, example 2. This one says find dy dx for the implicit relation y to the 4th plus x cubed y to the 5th minus 2x to the 7th is equal to 13. All right, this is definitely a little bit more complex. You'll see in the previous example, if I had wanted to, I could have solved that equation for y. If I just jump back there real quick, I could take this equation, x squared plus y squared, and solve this for y. Subtract the x squared, take the square root of both sides. You'll have a plus or minus the square root of something. You could solve that thing for y. Okay, and then you could follow your rules for derivatives of an explicit relationship. With example 2, we jump now to an equation which you are not going to be able to solve this for y. There's no way to isolate y here by itself. So given that fact, it's an implicit relationship. There's nothing you can do to change that. The only method we have to find its derivative then is using implicit differentiation. All right, so let's do that. So we're going to take the derivative. I'm going to go ahead and write this out. We're going to take the derivative with respect to x of y to the 4th plus x cubed y to the 5th minus 2x to the 7th, and that equals 13. We're taking the derivative of that whole equation. Take the derivative of both sides. The right side is the easy part. Derivative of a constant, that's going to be no problem. The left side is where the work is going to be done. So notice, first of all, you have a sum of 3 functions, y to the 4th, and then x cubed y to the 5th, and then a negative x to the negative 2x to the 7th. So we have the derivative of a sum of functions we know is equal to the sum of the derivatives. So let's follow our rule here to do this. Derivative, take the derivative of the first function, y to the 4th. And again, think of chain rule. Anytime you see a y that shows up in there and you're going to take the derivative of that, use chain rule. That'll help you get the y prime or the dy dx to show up properly. So the derivative of y to the 4th is going to be 4y cubed. That's derivative of the outside, evaluate at the inside, times the derivative of the inside, y prime. I'm going to write it as y prime, and again, as you do that, you can see that you need to make sure that you are not writing down y to the first power at all then in this problem. You just write those as y's, and only y primes will have that markup there. All right, that's the derivative of the first function. We add that to the derivative of the second. Now look carefully at what kind of function you have here. This is actually saying take x cubed and multiply it by y to the 5th. That's a product. If I want to find the derivative of a product, I've got to follow product rule. So let's go through product rule with this. Derivative of x cubed is 3x squared times the second function, y to the 5th, plus the first function, which is x cubed, times the derivative of the second, derivative of y to the 5th. Again, follow chain rule as you do this. It's going to be 5y to the 4th, that's derivative of the outside, substitute in the inside, times the derivative of the inside, it's y prime. And then derivative of the last function there, derivative of 2x to the 7th, that's actually pretty easy, I guess, in comparison to what we've done so far. So negative 2x to the 7th becomes a negative 14x to the 6th. Excuse me, x to the 6th. And on the right side, again, I've taken the derivative of the left side, so I have to do the same thing to the right side. Derivative of a constant, of course, is 0. Like I said, that's the easy side. Basically, what you'll notice is anytime I went to take the derivative of y, I get a y prime that shows up. So in this term here where I took the derivative of y, I got a y prime. And then the second half of product rule right here, when I took the derivative of the y term, or it's really the y factor there, I got a y prime. And those are the two terms that involve y prime. So I want to keep those over here on the left side, and I'm going to end up moving everything else over to the right side. So I've got 4y cubed times y prime plus, I'll write the 5 out front, 5x cubed y to the 4th times y prime. And I'm going to move everything else over to the right. So I'm going to have a negative 3x squared y to the 5th. And then adding the 14x gives me plus 14x to the 6th. Now on the left side here, again, the goal is to find out what y prime equals. So on the left side here, each one of these terms has a factor of y prime. That's why I left those two terms over here on the left side, and only those two terms. So we're going to factor out the y prime. So you're left with a 4y cubed plus 5x cubed y to the 4th. And over on the right side, nothing changes. Negative 3x squared y to the 5th plus 14x to the 6th. One last step here to solve for y prime, just divide by this factor. So the terms that we have over on the right side stay in the numerator part of this. We'll have a negative 3x squared y to the 5th plus 14x to the 6th. And that's all divided by, my board just stopped for a second. There we go. That's all divided by this factor that was on the left side. That's 4y cubed plus 5x cubed y to the 4th. Now, if there's obvious things that you can do to simplify this, I'd say you could do that, but for the most part, you can leave it right like that in that form. There is our derivative. And that's as far as we're going to go in this section for right now.